Okay, well, happy Wednesday. Today we're going to be having a brief discussion about vectors. So just as a reminder of some of the things that you may have learned before, we're going to go over what a vector is, what you can do with it, and why it might be helpful. So first and foremost, I like to think about vectors as arrows, right? So when you think about your vector, you often think about a magnitude, a length. And so for this one, the length is the length of the arrow. The direction is for how it's pointing. So in this case, kind of up and to the right. You know, we use vectors a lot because they not only do they show up, but they're useful geometric ideas. Vectors can move around. So I can take the same vector and I can translate it up or down and around. And as long as I don't change the direction, that is, if I don't change the angle, or if I don't change the length, it's the same vector. Now, when we talk about adding vectors, maybe I have one vector that looks like this, and I want to add it to another vector. So again, this vector is the same, this blue one, as long as I don't change its angle or its length. So we add head to tail. And so if I want to add up these two vectors, let's say this vector looks like this, I would add it head to tail. So I put these two together, and if I wanted to add them up, then what I would do is I would take the beginning of this vector, somewhere like this, to the end of this vector, okay, and I draw a line between those. At least I got the point on there. And I would draw a line between them, from the beginning of one to the end of the other. And this would be the sum of those two vectors. Okay? So we can add up vectors in a lot of different ways. I encourage you to take a look at slide 37. Or take a look at page 17 from your text. One of the things that we're going to want to become really good at is working quantitatively with those vectors. So in addition to thinking about vectors as arrows, we think about them in terms of their components. So as a quick reminder, something that I hope is a refresher. Let's pretend like I have some vector. I'm going to call this vector A. We usually indicate vectors with little arrows on the top. Now, I want to break this vector down into components. That is, I want to know how much of it points in the x direction, that is to the right, or the y direction, that is upward. So I identify my coordinate system, and then what I'm going to look for is I'm going to look for how much of this vector A points in, say, the x direction, which in this case would be that one. I'm going to call that AX. Or how much it points in the y direction. I'm going to call that AY. Now, let's pretend like this is some position vector. So the magnitude of A is going to be, say, 10 centimeters. It's a length. Okay? Let's pretend like I know this angle, right? Let's say it's 30 degrees to the x-axis. Don't forget about SOHCAHTOA, right? You would have learned this, I'm sure, at some point in high school. But if we want to find these various components, we use the sine, the cosine, or sometimes the tangent. So if I want to say find, I don't know, AX, okay? This is the adjacent side. This is the hypotenuse. So the cosine, in this case of the angle 30 degrees, will be my adjacent side, AX, divided by the magnitude of my hypotenuse. That would be the magnitude of A, which would be 10 centimeters in this case. You have to refresh your memory a little bit about what the values of the cosine are. We'll go over those. If you want to find, say, the vertical component, don't forget that that would be the sine of 30 degrees. That's the opposite. That's AY divided by the magnitude of A. Okay? If these things seem a little bit mysterious to you, please make sure that you go over some of the examples, slides 1.5, 1.6 in the PowerPoint for this chapter are pretty good. Make sure that you go over this stuff so that it's not mysterious to you. Another topic that we're talking about is the idea of displacement. So displacement is an important idea. Right, I'm going to start thinking about one-dimensional or 1D displacement. When we think about displacement, we're talking about the change in a position, okay, particularly in 1D. So the change, delta x, is going to be where I end up, my final x position, minus my initial x position. This is something that I want you to pay close attention to. We're going to be using these quantities a lot. Okay? We're going to use something called the particle model. Okay? And so in the particle model, one of the things that we're going to imagine is that physical objects occur as points. We're going to represent them as points. So in figure A here, we're thinking about a car slowing down. Well, instead of thinking about the whole car, we think about these points. Okay? So in part B, we're going to replace the car with these points. The numbers show in what order these frames are taken. Okay? In these particle models, we're going to assume that the time between each point is the same. So that's very helpful because it allows us to think about velocities or speeds. In this example, when two runners jog along a track, we can figure out which one of these runners is going faster. The time between each one of these points is the same. And so if the displacement is larger for a given time interval, then you know that runner is going faster. Make sure that you can do this example on your own. Now, the concept of displacement isn't just a one-dimensional idea. It's actually a two-dimensional idea. So let's imagine, for example, that we have a ball that we're throwing in the air. And so the ball maybe looks like this. We've thrown it up, kind of comes to the top, and then comes back down. Now, my details are probably a little bit off. But what I'm going to do is I'm going to call this point my origin. I'm going to define a coordinate system where this is the y direction, this is the x direction. And I can think about a displacement vector as well. Okay? So I have several time intervals here. My ball is traveling through the air. I imagine that each one of these points is taken with the same time interval between them. And if I want to think about a displacement vector from the origin, well, let's call this one 0, 1, and 2. And if I wanted to draw the displacement vector, I draw it from the origin, and I go to the point. And so I might call this R2, my displacement vector, to that second point. I do the same thing for all of these points. 2, 3, 4, let's say 5. I want to go to the fifth one. I do the same thing. I draw it from the origin to the point, and I might call that one R5. Okay? But the notion of a displacement applies to two dimensions as well. Okay? I strongly encourage you to think about these. Think about how we go from two-dimensional vectors to their components. Okay? If it's not clear, come and chat with me. I would do the integrated example. I think there's one on page 23 that's really good. Okay? The next concept that we're going to be talking about here is velocity. Okay? So again, these are two-dimensional vectors, but know that the reason why we write a coordinate system down is so that I can imagine their x and y components. So for instance, this vector R2, it has an x component that looks like this length. I'm going to call it x2. It's the x position of that vector. And I have the same thing over here for the fifth one. And this is a longer x position, so I'll do x5 here. Okay? So if I want to imagine what my average x velocity is, I'll do it over here. Average x component of the velocity. That is, Vx is going to be the change in my x position, the x displacement, divided by the time. So if I want to know what my average velocity was between these 2 points, this would be my final, x5, minus my initial, x2, divided by whatever that time interval is. These are important ideas, okay? Again, if this is a bit mysterious to you, take some time and review. Work out the problems, and then come and chat with me. The examples from the text are pretty good. I would do 1.8. That's on page 21. But the key idea is we're going to lay some foundation, okay? So don't breeze past ideas that are tricky. Don't be afraid of the mathematics at this point. We just have to get a firm footing so that we can